replacement reactions. A double replacement reaction occurs when two aqueous solutions exchange, or sometimes instead of the word exchange, I like to use the word swap. So they exchange or swap cations to form two different compounds. So if you were to look in a textbook for a general equation, you would have compound AB put into contact with compound CD. And if you remember cations from our nomenclature, the first partner in each compound is a cation. So A and C are swapped between the two compounds. As a result, A now forms a compound with D, so we have compound AD, and then the other compound forms between the anion B and the cation C, so we have compound CB. Now for us, we're going to keep it simple. A double replacement reaction will only occur if one product forms as a precipitate. Now, when you get into higher levels of chemistry, there's other things that you can look for. But for us, we're going to stick with if a product forms as a precipitate. So in order to figure out the phase of a product, we have our table F. So table F, it can be a little bit difficult at first. So table F is made up of two mini tables. So table 1, table 2. So when you're using these, the first column in each of the tables, this is where you start. This is the reference point. So I'm trying to outline this in blue. And then the other first column. So let's write down some ideas about what these captions mean for each of these tables. So these ions, when they are a partner in a compound, they typically form soluble compounds. That means that they tend to dissolve. So if they are formed in a reaction that occurs in water, their phase is going to be aqueous. The second column of that table is about exceptions. Well, this table is about things that are soluble or will dissolve. The exception would be that they are insoluble. They will not dissolve. So that means that their phase will be a solid because they form as a precipitate. Now, when we look at the second table, the header description is a little bit different than the first one. Okay, so here it says that they're insoluble. So insoluble means that they don't dissolve. So I'm going to write not dissolve. And because they don't typically or easily dissolve in water, these guys typically form compounds that are in the solid phase, even if they're formed in water, because they form as a precipitate. But notice, they have some exceptions. The exception, or the opposite of insoluble, the exceptions are when they will dissolve. And if they will dissolve, then these exceptions, their phase will be aqueous. So this is the process of learning how to use this table. So here we go. Our first example is CuNO3. So take a look down the blue highlighted columns. Do you see Cu in either of these columns? No. So find its partner NO3. And if you take a look, here is NO3 nitrate. So this is the one that we found in the blue table. Nitrates are typically soluble. So I'm going to write dissolve. So compounds containing a nitrate typically dissolve in water. And when you take a look over in the exceptions list, is Cu an exception? No, it's not an exception. So Cu, I'm going to write not exception. So it typically dissolves. This is not an exception. So that means that this compound, when it forms in water, its phase is going to be aqueous because it will dissolve. So we're going to follow this pattern. So now our next example is PbCl2. Pb, I don't see it in this blue list, and I don't see Pb in the other blue list. So now I'm going to look for Cl. And when I look down, oh, right here is Cl. So Cl, if it's in a compound, it is typically soluble. So I'm going to write, so Cl, it typically will dissolve. When I take a look, there are exceptions. So now what I have to do is I have to take a look. This partner bonded to the Cl is at one of the listed exceptions. And right there it is. So this makes it an exception. So chlorides typically dissolve, but this partner makes it an exception. So PbCl2, its phase in water is solid because it forms as a precipitate. Next example. So I have a partner Ca and an example PO4. So when I look down this list, I don't see Ca or PO4. When I go and look at the next list, oh, I found PO4. So I'm going to use PO4. So PO4, I found that in one of the blue ones, and PO4 is typically, if it's present, it's typically insoluble. So I'm going to write not dissolve. So PO4s don't easily dissolve in water. Are there exceptions? Yes, there are exceptions. I have to determine that partner Ca is it one of the exceptions or not an exception. Now, when you take a look at the exceptions in this second table, you will see group 1 and ammonium. So let's write down a little note here. So group 1 is pretty common here. You see it in all of these. Well, take a look at your periodic table and identify some group 1s. Examples of group 1s would be Li, Na, K, and Rb. Ca is not a group 1, so Ca is not an exception. So phosphates typically do not dissolve. Ca doesn't make it an exception to that rule. So calcium phosphate, this would be in the solid phase, and if it forms in an aqueous solution, it will form as a precipitate. Last example for table H, we have this solute, okay? So we're going to either look for Ba or OH. I don't see Ba in this list. I don't see OH in this first blue list. So I'm going to go over to the other column that's highlighted in blue. I don't see Ba, but I see OH hydroxide. So here we go. So hydroxides, OHs, because it's in this column, they tend to form insoluble compounds, so they tend to not dissolve. So what we have to figure out, what OH is bonded to, the Ba, is it an exception or not an exception? So when we look over here, the exceptions that make OHs soluble, group 1 ions, Ca, Ba, Sr, or ammonium, and there is Ba. So Ba, it is an exception. So since BA is an exception, if this substance forms in water, it will remain dissolved. It will be aqueous. So take a look. We have an example of a double replacement reaction. Barium chloride reacts with sulfuric acid, and as a result, barium sulfate and hydrochloric acid are formed. This reaction is not naturally balanced because I can see that I have 2 Cls on the left, but only 1 on the right. So I need to raise my Cl count on the on the product side. So I'm going to put a 2 here. So when I do that, it raises my Cl count from 1 to 2. So now I have the same number of Cls. It also affects the H count on the product side. So my H count went from 1. Now it's 2, but I see that there's already 2 on the reactant side. So everything else is balanced. Now, the job here is these are the 2 products. One product will be in the aqueous phase, and the other product will be the precipitate in the solid. So the product phases, it's double replacement, so which is the solid because it's precipitate versus which is aqueous. So we have to figure these out. So I'm just going to start here with BaSO4. So when I take a look here, I don't see Ba here, but I see SO4. So SO4s typically dissolve. And now what I have to think, Ba, is it an exception or not an exception? So sulfate, look at those exceptions, and Ba is an exception. So Ba is an exception to when it will dissolve. So when BaSO4 forms as a product, this forms as a precipitate. So the barium sulfates phase would be solid. Now I need to do the same type of thought process with the other product. So I'm going to look for H or Cl. I don't see H, but there is Cl. So Cl chlorides, they typically dissolve in water. I see that there are some exceptions, but is this H an exception? So when I look, it's not an exception. So chlorides typically dissolve. This is not an exception. So the HCl, as it's formed, it will remain aqueous or dissolved and blended in the water. So this is definitely a double replacement because one product is a precipitate and the other one remains dissolved. The last equation or type of reaction we're going to look at is the combustion reaction. So a combustion reaction occurs when an organic compound burns in the presence of oxygen to form carbon dioxide and water. So a general equation. I'm going to represent an organic compound. Its formula will start with carbon. N just represents the subscript. It'll immediately be followed by hydrogen. I'm going to say that its subscript is 2N. This organic needs to be in the presence of oxygen, and in the complete combustion, carbon dioxide and water are formed. Combustion reactions are always exothermic. They're a burning process, and burning releases heat. So you'll always see, if you need to talk about energy, it'll always be on the product side. So if you take a quick look at this reaction, take a look. This formula, you see it starts with carbon, immediately followed by hydrogen. So this is what an organic formula will look like, with oxygen forming water and carbon dioxide. Go ahead and balance it. I have 4 carbons and only 1 here, so I could probably put a 4 here. Now my carbon count is the same. I have 12 oxygens on the left, but only 2 on the right. So to raise that up by 12, I'll put in a 6. But now I gotta think about my oxygen count. So I have 6 oxygens from all the waters, plus 8 oxygens from the carbon dioxide. So I have a count of 14 oxygens. But on the left-hand side, I only have 2. So I need to raise that to 14. So if I put a 7 in front of the O2, that will make my count 14. So the organics coefficient is understood to be a 1.